Our last speaker before the coffee break is Hannah Rudiser on automatic detection of ICMEs.
All right, so thank you very much for the opportunity to present our work. My name is Hannah Rüdeser, and I'm a first-year PhD student at the Austrian Space Weather Office in Graz. And today I'm going to talk about the automatic detection of interplanetary coronal mass ejections in solar wind in situ data. To give you a quick overview about what I'm talking about today, first I'm going to start by reminding you about the features interplanetary coronal mass ejections typically exhibit and what the challenges may be when we try to automatically detect them. Then I'm going to go on to the machine learning part. I'm going to talk about medical image segmentation and how that relates to our specific problem here. And in the end, I'm going to present you the results of our work. And also I'm going to give a short outlook on what's going to happen next. Okay. So you probably all know that CMEs are one of the key drivers for space weather. And when we try to observe them in situ data, we can see that they might exhibit certain signatures. One of these signatures is, for example, a smooth rotation of the magnetic field and a totally enhanced magnetic field that you can see here in the top panel. Another one might be a proton density decrease after an increase during shock and sheath region. I'm saying they might exhibit these signatures because, in fact, not all ICMEs exhibit all of these signatures, and there is not a single signature that is present in all ICMEs. So this fact is also represented when we look at the number of catalogs that there exist. So we have a huge variety of catalogs, and all of these catalogs have different total numbers of CMEs per year. And experts do not only disagree about whether a CME, whether a certain event might be a CME or not, but they also disagree about when it actually starts or when it ends. So these are already some of the challenges that we face when we try to automatically detect them. As you can see, so one of them, as already mentioned, is the fact that we have many different catalogs. Not all events exhibit standard signatures. What is more is that we have a high variability in duration. That means they typically last around 20 hours, but some of them only last a couple of hours, and others may last up to almost 100 hours. What is more, start and end time are not clearly defined, and also ICME events are pretty rare, meaning most of the time nothing happens, we just have the background solar wind or even other signatures within the solar wind. So all of these reasons make it quite difficult to make sort of an automatic detection algorithm for that. So simple threshold-based algorithms are usually not enough to reliably detect ICMEs. So this is also why we decided to look at machine learning. And we specifically looked at biomedical image segmentation. We already had a talk where units were mentioned yesterday, but I quickly want to remind about the main facts when it comes to units. So they're typically used in biomedical image segmentation. So here we have a picture of a cell, or we have areas in these pictures that do not contain a cell, but we also have areas where a cell is contained. And the goal of this problem is we want to create segmentation maps where we segment each pixel into one of two categories, meaning cell or not a cell. So basically, this problem is a problem where feature information is as important as spatial information, meaning we do not only want to know if a certain picture contains a cell, but we also want to know where exactly is the cell. So the unit is an architecture that has proven very successful in these tasks. And they get its name, obviously, from their U-shape. But what happens is that we have an input image, and we want to create an output segmentation map. And we have a downward path, and throughout this downward path, we reduce the spatial dimension and we increase the feature dimension of our information. And in the upward path, the decoder, we reintroduce through concatenations this spatial information. And we also, once again, increase the spatial dimension and reduce the feature dimension. Okay, so you may ask yourself, what does that have to do with detecting CMEs? Well, what we did is we reformulated our CME detection problem as a time series segmentation problem, because we figured out we have a problem where feature information is as important as spatial, in this case temporal, information. So what we do is we have a time series and we segment each time step into one of two categories, ICME or not ICME. So as you can see here, the black bars indicate a CME, and the spaces in between is a region in time where no CME has taken place. Okay, so we did not use exactly UNet. We used a variation of a ResUNet++, which is sort of a more advanced version of a UNet. Basically, the U shape stays the same. We still have an encoder and a decoder, but the simple convolutional units are replaced by residual units, which basically facilitates learning throughout the network and increases performance. If you're interested in taking a closer look at the code or want to play around with it yourself, all of our code is openly available on GitHub. And I don't want to go into too much detail of the technical details. So yeah, let's take a look at the results. So you can see here in the middle panel the true label, meaning the label that was created from a catalog. And below that, we saw what our pipeline predicted. So as you can see, there are some events that we didn't capture, and there's also this one where we had an additional event that was predicted by our pipeline. And of course, just looking at that, we cannot see how good the performance is, but we can definitely see that our pipeline is able to highlight areas of interest. So our next step was to convert this binary label into a catalog, and then compare the catalog to the ground truth catalog. When we did that, we also were able to make an estimate of how well we represent, we predict start and end time. And as you can see, we have some events, like this one here, where we almost perfectly reproduce start and end time. We have some where we match start time, but do not really accurately match the end time. And also we have events where it's the other way around. We do not really predict the start time, we predict the end time. And we looked at the total number of events, and we figured out that we had a mean absolute error of 2 hours and 56 minutes on the start time and 3 hours and 20 minutes on the end time. If we think about possibly using this pipeline in the future for real-time detection, of course, accurately predicting the start time in an in situ catalog might be valuable. Okay, so we also, of course, wanted to take a look at the actual prediction rate. So we looked at a period in time where we had a total of 640 ICMEs that were part of the catalog. And our pipeline predicted a number of 720 over this period. So we predicted more events than there were actually. And if we take a closer look at how this is split up, we can see that we have 466 true positives, meaning events that were part of the catalog and that were also predicted by our pipeline. We had 174 false negatives, meaning events that were part of the catalog but our pipeline didn't manage to predict them. And we had 254 false positives, meaning events we predicted but that weren't actually part of the catalog. So what we did then is we wanted to understand, okay, why is the prediction rate not as great as we hoped it would be? And we took a closer look at false positives and false negatives. And you can see two examples here. So we have a false negative here and a false positive here. And we realized, for example, here, one feature that is often present in ICMEs is a low plasma beta. And as you can see here in this false positive, we have a very low beta parameter compared to the surrounding solar wind, meaning this would actually be a signature that could be indicative for a CME being present. While this, for example, the beta parameter isn't as low compared to the surrounding solar wind. So what we figured out is that actually the ground truth that we learned from might not be perfect, which is also represented by the fact that we have so many different catalogs, so even experts disagree. And of course, this is a problem that we always have with supervised learning. If there's bias in the ground truth, we will probably make the network learn this bias. So what we figured out is that some of these false positives might actually be at least CME-like structures, and some of the false negatives might be CMEs that don't have all of the signatures, so it might not be a clear CME. Okay, so we now decided how can we really want to like make the performance better. So what can we then do? One of our next steps is that we really want to try to make a real-time implementation of this pipeline and use it on real-time solar wind. Of course, we have to check out if that works because we have some data gaps in the real-time data. Then we also need to answer some questions in order to figure out whether we can really use this in a real-time fashion. One of these questions would be how much of the ICME needs to be seen by the algorithm to trigger the automatic detection? Meaning if we only see the shock in the sheath, is this already enough for the pipeline to say, okay, this might be a CME approaching? Another question that we ask ourselves is, can we improve the detection rate by focusing on events that exhibit a clear shock in sheath region, so only on very definite CMEs? We also thought about introducing a probabilistic label by making use of the different by making use of the different catalogs that we have, or for example, letting different models vote. And we also thought about whether we could make use of information of, for example, HI images or other information closer to the sun. So for example, if a CME is seen close to the sun, the probability that we also detect it in situ is probably higher. Something that is probably more of a long-term goal is that we would hope to also be able to forecast the duration of a CME with the pipeline. And of course, there's always the question if we can improve the detection by using other machine learning methods. So to sum up, this work has recently been published in the Space Weather Journal, which you can see here, and the QR code leads you to the paper if you're interested in learning more about the details. So to sum up, we have Resonate++, which we used for the automatic detection of ICMEs. On wind data, we detected 466 out of 640, although I want to mention that during the work that was then published, we also tried the pipeline on stereo A and stereo B data with slightly less great performance, but still we managed to detect some of the ICMEs. So if you're interested in looking at how it performs with other data sets, you might want to check out the paper. We have a mean absolute error of 2 hours and 56 minutes on the start time, which is relevant when we think about real-time implementations. And of course, this is work in progress, so we want to work on a real-time implementation. We also want to try to combine this with other models, and we hope that label improvement will then eventually lead to improving our detection rate. So yeah, thank you for listening and for your attention. I'm happy to take any questions.
Okay, we have one question in the back.
That was great, thank you. Have you compared or thought about comparing your results for ICMEs with interplanetary type 2s from radio data from wind or something like that?
Not yet. That might be something for the future.
Okay, yeah, because I don't know how it works for interplanetary type 2s, but I'm fairly certain for coronal type 2s, every single coronal type 2 is related to a CME, but not every CME is related to a type 2. So I don't know if the same thing works for you.
Yeah, that might be interesting to look at in the future. Thank you.
Yes, in the front.
Very nice presentation, thank you so much.
Thank you.
I was wondering how many input parameters you use for training.
Yes.
And just adding to that question, if you find any specific parameter that can be related to the results based on the different catalogs. Probably the authors focus on specific parameters to define the ICME.
So I have an additional slide on the features that we used. So we tried two different sets of features, or one we called the full data set and one we called the reduced data set. And what was really interesting is that we thought that the parameters present in the reduced data set would probably be enough to accurately detect CMEs, but for example, the 15 canals of proton flux present in the full data set definitely made a difference when it came to the detection rate, which wasn't used, at least by the person who does the ICME catalog in our group. He says he doesn't look at these because he thinks looking at magnetic field and some of the other more obvious parameters is enough. So we definitely want to, this is also something we want to look at when trying to create different models that get sort of a vote. Maybe train them on different catalogs and different features, try to see how that works, but that is something that we still have to do in the future.
Thanks for the nice talk. I think I didn't understand how do you compare the results of your pipeline with the observation, because you mentioned that you have the different catalogs, they have different results. For example, in the number of ICMEs that are detected. So how do you compare exactly?
Yes, so also we used a different catalog for the full data set. In the end, that was published then, and a different catalog for the reduced data set, because for stereo A and stereo B we only found one catalog that was present in the full period. So what we did is that we compared it to the catalog that it was trained on, and because we wanted to figure out whether it was able to reproduce the catalog that it was trained on. Comparing the two catalogs, so the catalog that was sort of the ground truth and then the catalog that was predicted by us, we classified it as a true positive if there was an overlap of more than 60% between two events. But what we also did, I think you can see it here. For example, so what often happens is that one large CME might be classified as several small ones, or we might have a little gap in between. We would then, during post-processing, count this as one CME and allow it to just be the same CME. So this is how we then compared ground truth to our catalog. But of course, in the future, we have to even take a closer look at if we use one catalog to train, if then the false positives might be present in another catalog that we also have. So this definitely will require some more work, because it's just there's just a lot of bias introduced when it comes to these catalogs.
Mm-hmm. So now do you use only one? So do you use only one catalog, or is it a combination of the catalog?
So we used one catalog that was a combination of all other catalogs, and also had some additional events that were introduced in 2019, but also using a machine learning pipeline. And what we did is we used a second catalog, and this catalog only included more certain events. So not every CME-like structure, but only CMEs that were part of more than just one catalog.
Okay,
so we had one more loose catalog and one more strict catalog that we tried to look at.
Okay, here's a quick question. Have you tried, because we know that most CMEs are flux orbs, have you tried any physical conditions in the magnetic field components that you mentioned, which in this case would be the rotation of the magnetic field vector, to try to see, because this could help you clean up your sample and improve your detections? Have you tried that?
Not yet, but we were also thinking about that and discussing it for possible future trial.
Yeah,
so,
that would be interesting to try.
Yeah, we also hope that will definitely, also like combining it with other more physics-based models might be interesting in the future.
Thank you.
Yeah, thank you.
Thank you. Thank you very much.
Thank you.